In this video, I want to talk about how to answer gravitational potential questions in A-level physics. And gravitational potential is fundamentally different from things like gravitational field strength and the amount of force that's exerted on a certain object. Because gravitational potential is all about the energy, the gravitational energy that a certain object has. So it has to be delineated from the graphs of forces and force fields and fields. And so that's what we're going to try to do in this video. So the first question is really simple. It's just asking us to define gravitational potential at a point. The definition of gravitational potential is the work done in bringing unit mass from infinity to that point. It's work done because it is energy. So something really fair for measuring the amount of gravitational energy something has is if you are next to any mass at all, let's see, these are like planets and this is you are in the gravitational field, and therefore there's a force exerting itself onto you and onto the planets. But if you are an infinite distance away from any other mass, that's when the force on you is going to be 0. So there's no force acting on you because you're an infinite meters away from any object. If we are brought back to the fields, that's when we actually start to gain energy. So this is the part where we say, let's assume that the potential here is 0. Now, being pulled here, you don't actually need to like push or pull because you're going to be pulled here naturally because of the gravitational attraction. And you have to actually do work to bring it away from this. So you have to do work to get it away from all of the mass, which means that over here, any point where you're not at infinity, you're going to have a negative value for your gravitational potential. So moving on, the second part is this question. There's a bit of math here. It says TESS is a satellite of mass 360 kg in a circular orbit around the Earth, as shown in figure 1.1. So this is our satellite, and it is the orbit. The radius of the Earth, then this is the Earth, obviously, and the mass of the Earth is given over here, and it takes TESS 13.7 days to orbit the Earth. So we need to show that the radius of the orbit of TESS is this much. So this is a question where we don't actually use gravitational potential. We're using the gravitational force here. The force is the centripetal force. So obviously the gravitational attraction is the centripetal force, and we have the formulas for both of them, so we're able to calculate that. First of all, before we do anything, let's get this. This is the period of TESS. Let's convert this into seconds so that it's easier to work with. So the period, let's put this as T over here, is 13.7 times, and we have 24 hours in a day, and we have 3,600 seconds in every hour. So if you calculate this, you'll get, this is the amount of seconds you're going to get. Now we have to claim that the centripetal force is actually provided by the gravitational force. And this is why we can claim that the centripetal force, F is mv squared over r, is actually equal to the gravitational force, which is gmm over r squared. So now all we have to do is move this around and do a little bit of algebra to solve what we need to get. So I've rearranged the equations so that we have r on one side of the equation, because at the end of the day, what we're trying to solve is the radius. Now all we have to do is to substitute the values into this. We have already found t, it's over here in terms of seconds, and then the m over here is given in the question, that is the radius of the Earth. So basically, the final answer you get after putting it in your calculator is 2.4 times 10 to the power of 8 meters. And we have basically shown the prompt in in our question, it just tells us to show that this is this answer. So we can write shown, and we're done with this question. So now let's really get on to the gravitational potential energy part. So over here, they tell you to calculate the change in gravitational potential energy between tests in orbit and tests on a launch pad on the surface of the Earth. So we have two positions here. We have tests over here, and we have tests on the Earth, and there is a different potential energy, and we want to find the difference of these two. So the first thing to think about in this situation is the formula for gravitational potential, which is phi equals to negative gm over r. So this is the equation for gravitational potential. And here I want to delineate between gravitational potential and gravitational potential energy. Gravitational potential is like a gravitational force field, but for the energy. So it's telling you how much a certain unit mass has, how much energy a certain unit mass has at a certain position. It is not the ultimate energy of the mass, but it is like telling you at this position, 1 kilogram of mass would have this much energy. So if you had 2 kilograms of mass, you would have to double that amount to find how much energy it has. So this is why the energy, the actual gravitational potential energy of tests, is found by multiplying the mass of tests to the equation that we had before. So we are going to use this, but I'm going to write both of these equations here. Now we can search for the delta E, which is the gravitational potential energy change, so between these two positions. And this is really easy to do. First of all, you get whatever you want. So let's get, this minus this, for instance. We can take the orbit of the radius of the orbit of Tess, and then we can minus it from the radius of the Earth. So we have two values here, and we just have to use these two. So we can go ahead and do that right now. And we obviously don't need the negative signs over here because both of them have negative signs, and we're just trying to find the difference between them. So it doesn't matter what the sign is, we're trying to find the magnitude of the difference. So I'm going to neglect the negative sign. So if you do all the calculations, this is the answer. I end up with 2.2 times 10 to the power of 10 joules. So I'm going to write that down over here. So we have our final part, and over here they tell us to use the information in B1 to calculate the ratio of the gravitational field strength on the surface of the Earth and compared to the gravitational field strength at the location of Tess in orbit. So again, let's just start with the formula. This is the formula for gravitational field strength. Now our ratio is going to be, Earth, this of Earth and this in orbit. So it's going to be GM over, radius of Earth, right? Over GM radius of orbit. Let's just denote it like that. And then, you do a bit of algebra and you end up with R orbit squared over R Earth squared. So all you have to do is to substitute the answers we got. The orbit is this value, and you square that, and then the Earth's radius is 6.4 times 10 to the power of 6 squared. So essentially, you get 1,410. That is our ratio, and there are no units because it's a ratio. So very simple question. So this is one type of gravitational potential question. There's another type of gravitational potential question that we're going to work on right now. Another noteworthy type of gravitational potential question is these questions where you have, two bodies, maybe you have a planet and a moon, and then you have gravitational potential graphs. And you have to analyze these graphs or maybe even draw a graph of your own, which we have which we have over here. So this is one that we're going to solve right now. So first of all, they tell us to state the relationship between gravitational potential and gravitational field strength. So as we've said before, we know that the gravitational potential has an equation that looks like this. Phi equals negative gm over r. And gravitational field strength is actually equal to gm over r squared. So you just have to divide it by r once, and then you will get gravitational field strength. This is what a potential gradient looks like. This is, I think you can call this r. The gradient of this is basically the potential divided by r, right? It's the y value divided by the x value. So the gradient of this graph is basically gravitational field strength, which is why we can say that the gravitational field strength equals the potential gradient with a negative sign. So you have to obviously multiply a negative sign to this to get rid of the negative sign. That's already on the potential. So we have our answer over here. Obviously, there are other ways to describe this relationship. You can say, oh, you have to divide it by r, but they are specifically looking for your knowledge of the gravitational potential gradient. And it's also a very easy way to visualize what is happening. Now let's move to the second part. There's a moon of mass m and radius r, and it orbits a planet of mass 3m. So this is 3 times more mass than the moon, and radius 2r. At a particular time, the distance between their centers is d, as shown in figure 2.1. Point P is a point along the line between the centers of the planet and the moon, at a variable distance x from the center of the planet. The variation with x of the gravitational potential phi at point P for points between the planet and the moon is shown in figure 2.2. So this is the gravitational potential gradient. How do you know that this is a gravitational potential gradient? The answer is that it doesn't hit 0. If this was a gravitational field graph, then at some point it's going to have to hit a 0, because the forces on P is actually being pulled in opposite directions. So if it was the gravitational field graph, then it's going to look something like this, where the closer you get to the moon or the earth, the field strength goes up. But at a certain point, it hits 0, because the opposing forces balance out and they basically cancel each other out, making the force and the field strength 0. So just by knowing that it doesn't hit the x-axis, you already know this is a potential graph and not a field strength graph. So this is a delineation that you need to know and understand quite well. So they gave us this nice little graph over here. We can obviously tell that this is probably the moon, because you have, more potential closer to the Earth because it is of a bigger mass. So let's see what they want us to do over here. They tell us, explain why phi is negative throughout the entire range of x is 2r to x is d minus r. By the way, I want to say x is 2r means this, because radius is 2r. And then d minus r is over here. Obviously, this is r. So they're just telling us this is like what's going on along the x-axis, if you can see that. All right, so they tell us, y is a negative throughout the entire range. And they're asking you for what I just said. Why doesn't it hit the x-axis? This is because it's gravitational potential. So here's what I would write for my answer. So this is the first part. And remember, we have 3 points over here that we can earn. Phi gravitational potential is only 0 when it is at a distance of infinity from any mass. That's mark 1. The second point comes from the statement, when it is in a potential well, like it is right now, it has a negative value. So that's mark 2. So finally, the third part of this is explaining why it has a negative value. And this is the explanation. Since gravitational force is attractive, as mass gets closer from infinity, the potential energy will also become lower. So that is how you get your full 3 marks. The second part asks us to describe 2 other features of figure 2.2, which is what we have over here. So this is figure 2.2, and they just want us to describe more features of it. And they tell us one of that is that, phi is negative throughout, and we just have to note other qualities. So the first thing that we can comment on when we look at this is the maximum potential, which is like somewhere over here. And remember, this is the moon and this is Earth. The maximum potential is closer to the moon than it is to the planet. So we can comment on that first. And remember, that's happening because the force of the Earth, or the potential gradient of the Earth, is much steeper than the potential gradient of the moon because of its higher mass. So if we see over here, this is exactly what they mean by it. We have like a potential gradient and it goes down like this to the Earth. And the maximum potential happens somewhere here. It's like a trampoline. Imagine a trampoline that's bending in 2 ways by the mass. The highest point of the trampoline is still not going to be like 0. Let's say this was a 0 level. They still have a long way to go. It's still going to be a negative amount, but the maximum it's going to be is going to be closer to the moon because this is so much steeper. So that's kind of what, I mean by that. Second observation you could make is you could also say that phi is inversely proportional to the distance from the planet or the moon. Because of the fact that obviously the equation itself tells us it's over r, right? So you could also comment on the inverse proportionality. You can also comment more things. For example, you can also say that the potential of the surface at the planet is smaller than that at the moon, because obviously the planet has more mass. You can also say that the potential gradient at the planet is bigger than that of the moon, because obviously the planet has more mass. So you can compare the planet and the moon together. I think that's where you really get like a gold mine of answers and points that you can make. So finally, they want us to sketch the variation with x of the gravitational field strength G at point P between x is 2r and x is d minus r. So we have G over here, which is, let's say this is the gravitational field strength at the surface of the planet. The gravitational field strength at the surface of the moon has to be 1/3 of this because of the fact that the mass is 1/3 of that of the planet. Remember that it's mass 3m versus mass m. So and also it's going in opposite directions. They're pulling in opposite directions. So one is going to be in the positive part of the y-axis. So one is going to be, remember this is 1/3. So G has 3 of these small squares. So to get 1/3 of that, we're just going to go down by 1 small square. So this is kind of how it looks like. And then at a certain point P, let's just say it's like somewhere here, you can label P. It's going to hit 0, like I said. So it goes down like this, and then it would look something like that. And that's it. That's the variation of x with the gravitational field strength G. Now let's say that for the gravitational field strength, you did not want to actually put a unit on it, because gravitational field strengths usually don't have a direction. This is why we're going to recorrect this so that it points up again. Something like that. Because gravitational field strength, usually it doesn't really deal with like the direction in which it's pointing. So this could be the final answer for your graph. Now, if they wanted you to write down something for the gravitational force, then it would have to go in opposite directions because of the fact that force does require, signs to be attached so that you can know the direction. So that's generally how you answer questions like this, questions about gravitational potential It's really useful to think about the potential wells, think about like a trampoline and different masses kind of pressing down on the trampoline and making these potential gradients. So I hope this was helpful for you. And if you want very similar videos on how I solve past paper questions, you can check out the rest of my channel. If you want information videos about gravitational potential, where I explain the theory of it, you can also check out my channel for that as well. But overall, thank you for watching and have a good day.